I don't record the summaries, I just record whatever we lecture. Well, so that's the second derivative, d squared y dx squared. Okay, it's not just taking a second the derivative of the derivative like we did in rectangular form. So it's a little bit more than just that, d dt, and of the already first derivative with respect to x, which is a function of t, divided by dx dt. And all these two quantities, we got them from the previous part. All right, so let's see. dy dx is this derivative here, dy dx. So d dt of 3t squared over 2t minus 1 divided by dx dt, which is also 2t minus 1. All right, careful when working with this right here. All right, so number one, we're going to use the quotient rule to go through the numerator. How about we recall what the quotient rule is? Careful, because the quotient rule involves finding a difference in the numerator, and order matters with a difference. So u over v prime, that's u prime v minus v prime u. The whole thing divided by the denominator, v squared. So let's apply that to the numerator. In other words, what we're going to do here is find the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. And, well, so that's going to be the derivative of the numerator. That's a 3t. No. That's a 6t times 2t minus 1 minus the derivative of 2t minus 1, which is 2. Whoops. And times 3t squared. The whole thing divided by the quantity squared, the denominator squared, 2t minus 1. And careful, because we're dividing this whole thing by the quantity 2t minus 1, which is dx dt from the formula for the second derivative. And that's 2t minus 1. And, well, so it doesn't look like a little weird fraction here. I would write a placeholder 1 right here and enclose that whole denominator with a fraction, because we're going to instead multiply by the reciprocal of that fraction. Again, dividing by a fraction is the same as multiplying by the reciprocal. All right, let's simplify this. I'm going to simplify the numerator using the distributive property. 6t times 2t, 6t times negative 1, and 2 times the quantity 3t squared. And that's 12t squared minus 6t squared, and divide that by number 1. Careful. 2t minus 1 quantity squared, which is the denominator of the fraction in the numerator, and then I'm going to multiply by the fraction right here, by the reciprocal of that fraction, which is 1 over 2t minus 1. Actually, I'm going to highlight this just so you can later see how this is turning to you. All right. So there's a couple of things we can do. Combine like terms in the numerator and multiply powers of 2t minus 1 in the denominator. That's going to give us the quantity 6t squared minus 6t over 2t minus 1 quantity cubed. And, well, even though we can factor out a GCF in the numerator, that's really not going to help anything to simplify the whole function, the whole derivative. So let's call it final answer here for the second derivative. Okay? Well, so we're going to use this second derivative to determine the concavity of the function at a point where t equals to 2. So this is what we do. We will simply evaluate that second derivative when t equals to 2. All we do is replace the letter t, whatever, the number 2, whatever you see the letter t, in the second derivative. Now, so this is 6 times 2 squared minus 6 times 2 divided by 2 times 2 minus 1 quantity cubed. All right, let's do one operation at a time maybe. Well, so what do we have? 2 squared, which is 4. 4 times 6, that's 24. 24 minus 6 times 2, which is 12, that's 12. And in the denominator, what do we have? 2 times 2, which is 4, minus 1, that's 3. But that number, quantity cubed, that's 27. This number reduces to 4 over 9. Even if you don't reduce it, all we care in this case is the sign of this value. But I mean, if you reduce it, that's fine. It would be great if you reduce it, but ultimately we care about the sign. So because in this case, f double prime is greater than 0, that means, is that concave up or concave down? Question for anyone? Concave up, right? Concave up, right? That's a happy face, right? Otherwise, concave down, it's a sad face, right? So, and well, so this concludes the differential calculus part of parametric equations, right? So for the next application, the next calculus operation is it has to do with the integral, and we're going to use it to find the area under a curve defined parametrically. And well, it's very similar to what we did back in rectangular form. That is, just integrate f of x between a and b. I mean, that's simply the definition, the geometric definition of the integral. And in this case, well, so since we have this a function in parametric form, all we do is, well, I don't want to go through all the details. It's going to be a little convoluted if we went to see all that. So that becomes simply the product between g of t, which is the y equation, times the derivative of the x equation, x prime, right? So let's go ahead and look at one example. Then we're going to look at the graph of what we are finding the area for. You'll see. So, well, I have attached a picture of it in the PDF file. And for those of you who printed it, or you have the handout print on your tablet or your laptop. So this kind of function is called a cycloid. All it does, it's like bouncing, having like particle bouncing periodically by multiples of 2 pi based on the radius of that semicircular type of shape, And well, so we're going to look at the area of one of these arcs, below one of these arcs, not the whole thing. And well, so all we have to do here is find the derivative of the x equation. So that is, let me go through the derivative of the x equation, dx. And although, check this out, although we describe these functions in terms of t, in general, when we introduce parametric functions in terms of thetas, in terms of mostly trigonometric functions, we change it to theta. But I mean, recall it's just a dummy variable. It's the same thing. It really doesn't matter. You can change it to I don't know, to an S or a T. Well, the S is going to have a different meaning in Calc 3. Well, I'd rather not use that one. But I guess theta is just fine, right? So dx d theta. Dx d theta, that's the derivative of theta, which is 1, minus the derivative of sine, which is cosine theta. And well, let's set up the integral that calculates the area for us. Area equals the integral from alpha to beta of, in this case, that's our g of t. G of t. Well, I'm going to stick to the definition for now, but notice we have the functions labeled differently. I'm going to point that out in a minute. Times f prime of t dt. Well, this is the integral from alpha to beta. The g of t function corresponds to the y of t function. And I'm going to highlight this just so you can see what this really is. G highlighted with y, and which is this y right here. And next is times, oops. Next is times f prime of t with dt, which in this case is the derivative. Oh, I'd rather use different color here. Oops, yes. This function that I'm highlighting here is going to be this f prime of t. All right. And oh wait, no, it's well. Let me actually go through. Hold on. Not f of t, but rather dx d theta, or dx dt. And well, in this case is this dx dt, but again, we're working with theta, which is the same, all right? So, well, so that's going to be the integral from alpha to beta. That's from 0 to 2 pi, which is just a quick comment about this type of exercises. These ones are going to be very straightforward. You will be given just a set of parametric equations and the limits of integration. I mean, there's really nothing weird about it. So that's a 6 times 1 minus cosine theta. That's the y equation, and times the derivative of x, which is actually happens to be the same, 6 times 1 minus cosine theta. And I'm going to change all the dt's with d thetas, okay? Because we're working with angles this time. Well, so that's the setup of the integral. So how about we evaluate the integral? Let's do a little bit of algebra and find the most suitable method to compute it. So number one, how about we get the constants outside of the integral? That is 6 times 6, which is 36. That's 36 times the integral from 0 to 2 pi. And that's 1 minus cosine, actually times itself, which I could write it like a quantity squared. Okay, let's see what can we do from here. Question for anyone: can we do a u substitution here? Why not? If we, what happens? What will we get if we get the? What do we get for the du if we u sub with 1 minus cosine? A sine. However, do you see a sine multiplying with the no, right? So in this case, u substitution just let us down in here. So we'll have to find another way. Well, so I guess in this case, I mean, we wish we had that sine multiplying, and the u sub will just stand like very, very nicely. So we have to find another way. So algebra, how about some algebra here? So we will have to use the binomial squared, obtain a polynomial in terms of trigonometric functions, and integrate term by term. And well, even though that sounds like, well, I mean, integrating 3 terms, that doesn't sound that bad. You'll see something here. So that's a 1 squared equals to 1 minus 2 cosine theta plus cosine squared theta. I'm using the squared binomial formula. But if you are used to do the foiling method, it's up to you how you do it. It doesn't matter. You should get the same result. All right? Well, so the integral of 1, it's just the theta. No issues with that. The integral of cosine theta, no issues with that one, right? I guess it's pretty straightforward. However, the integral of cosine theta, there's a little issue with that one, huh? Well, in that situation, we cannot just integrate cosine theta, but because of the same situation as before. If we said u equals to cosine, we would have to have another factor of sine, which stands the du part for cosine. And unfortunately, we don't have that in our setup right here. However, you might recall this something from not the beginning of the semester, maybe like throughout a month or so when we discussed the different methods of integration. And one in particular I would like to recall, it's the trigonometric integration, in which we used pretty much every single trigonometric identity possible available here to simplify this cosine squared, because, well, we cannot integrate cosine squared, but there's identities to help us simplify this well. I know it's been a while, so let's recall those identities well. Number one, you might remember I used to call these identities the power reduction formulas. However, pretty much every single textbook refers to these identities as the half angle formulas. Number one is for cosine squared theta, the other one is for sine squared theta. All right, let's see if someone remembers these formulas. Anybody remember any of these or both formulas? So what do we do for cosine squared to reduce its power? 1 plus sine squared over 2. All right, 1 minus sine squared theta over 2. So do we agree with these two identities? What do we disagree with here? It's 2 theta, right? Not well, number one, it's not sine, right? It's cosine, and that's a 2 theta, right? Not power. I mean, because if we still leave it as square, well, we're not reducing the powers, right? So we are actually leaving the powers the same. We would be adding more terms to the integral, well, so we're not going anywhere. All right, so in this case, well, we have a cosine square here, so let's use the formula for cosine squared. So in this case, I'm going to do a couple of things in one shot. Number one, I'm going to replace cosine squared with the identity. And that's 1 minus 2 cosine. Plus, I'm going to distribute 1/2 plus 1/2 cosine 2 theta. And this, just so we can combine like terms, which in this case, it's the constant terms right here. So 1 plus 1/2, that's just going to give us 3/2. So that's 36 times the integral from 0 to 2 pi of 3/2 minus 2 cosine theta plus 1/2, 1/2 cosine 2 theta, d theta. And now we have the three terms that we can integrate just directly. I mean, we can integrate 3/2, we can integrate cosine, we can integrate cosine 2 theta with a mini u sub right here. Well, even though it looks just really simple to integrate these three terms, how about we distribute the 36, because you don't want to get too complicated with these two factors. Okay, so I'm going to write this in terms of three integrals here. That is 36 divided by 2, that's 18, and 18 multiplied by 3, that's going to give us 54. So that's the 54 times the integral from 0 to 2 pi of d theta, minus 36 times 2, that's 72, times the integral from 0 to 2 pi cosine theta d theta, and 36 times 1/2, that's 18, times the integral from 0 to 2 pi cosine 2 theta d theta. I mean, if you already have a lot of practice with integrals, maybe you can do this in your head, but of course, I always recommend that you write every single step, all constant factors, write them outside of the integral, so you don't get confused when doing these mini u substitutions whenever applicable. Right, so let's just integrate term by term. The integral of d theta, what's that? Theta, right? The integral of cosine, sine times minus 72 sine theta plus 18. What's the integral of cosine to theta? Careful with that one.
Negative.
1/2. 1/2 sine 2 theta, right? The angle remains the same in this case. And well, everything getting evaluated between 0 and 2 pi. And well, let's do some simplification maybe. Well, I'm going to do it along the way. Now, check this out. Recall what we have been talking about throughout the entire semester. Well, the next step is to use the fundamental theorem. Well, evaluate the integral of the upper limit minus the evaluation of the lower limit. But notice the lower limit is 0. So in this case, what do we have? 54 times 2 pi minus 72 times sine 2 pi plus 18/2, which is 9 sine 2 times 2 pi. Okay, minus. Do you see what's going to happen when I plug in 0 for all these three terms? 54 times 0 is going to get zeroed out. Sine 0 is just 0. Sine 2 times 0 is just sine of 0 still. Big 0, all right? Big 0, that's fine. But even still, check this out. What happens with sine 4 pi? Isn't it also 0? Also 0. What is that again? Yep. So, which in this case is 108 pi. All right? 108 pi. So that's our final answer. All right. Now, to graph this function, so let me pause this a little bit and. All right, so when it comes to using the graphing calculator, you want to make sure of a couple of things, of course. So number one, you want to go to mode. You want to make sure your angles are in radian mode. And well, recall that there's a few ways to graph function. That's the function, the usual function y equals f of x, and which is the one that we have been graphing throughout the entire semester except for this chapter. And you might want to make sure that you have it in parametric form. In the next section, maybe next time, I don't think we're going to have time today, maybe, I don't know. Well, we're going to look at the polar system, but that's going to be something else. And that's a critical system in which we are going to graph flowers, hearts, Pac-Mans. Well, you'll see how those are going to look like. Well, so let's make sure that we have this in parametric form. And second quit, we go to y equals. So notice how our graphing calculator sets parametric equations by pairs, x1, y1, x2, y2, because in this case we're graphing parametric equations in terms of two equations. You know, one equation for the x direction and another equation for the y direction. Well, I already typed this one because I already did this one in the previous section in the morning. Just make sure not to overuse parentheses. Well, in this case, it's fine. 6t minus sine t, 6 times 1 minus cosine t. And well, first thing you do is click on graph. However, you're not going to be able to see the entire graph, unfortunately, because, well, most likely I have the zooms, the standard zoom, from negative 10 to 10, negative 10 to 10 on both axes, with the y-axis and the x-axis. However, if, in this case, notice the form of the equation, this is where our r is. R equals to 6, 2 pi times 6, that's a 12 pi. So we want to make sure that we have a window big enough so we can see the whole graph. That is, let me go to the window, and it's the x direction, the one that needs some attention. I'm gonna type a 12 pi and graph. And well, at least we're able to see the first cycle. However, not the entire thing. So you might want to also modify the y max. I'm gonna do 20 just to make sure, maybe. And that's our cycle. All right. Do you want to see more cycles? Because again, check this out. In this case, this is a graph that repeats. It's a periodic function, repeats and repeats many times. So number one, what I would like to do, I would like to set up this window for different values of t, so it graphs more cycles. In this case, is the t. In this case, I'm gonna do I'm gonna do from 0 to multiples of 12. Have about 36. Let's see 3 cycles. So 36 pi. But I would like to do the same on the x direction. 36 pi. And let's graph. All right. Now you will see the three cycles of the cycloid in this case, not just one. So in this case, for parametric form, make sure to modify not just the x window, but also the t window, which is actually the t values at which the particle will be in the x and y location. So make sure to have all that. All right. That being said, well, again, all I wanted to cover with this graphing calculator, just so when you're doing the homework and you are trying to look at how these graphs are going to look like, there's some bits that we need to modify, especially number one, the t and the x most of the time. But it's mostly the t. Okay. So that way you can see the graph of the whole thing. All right, now let's see. Let's go back. So that was one example, finding the area. The next topic for the integral calculus of parametric equations is that of finding the length of an arc, the arc length. And guys, you might remember this topic from maybe after, I think it was like a month and a half after we started the course, when we covered arc length in rectangular form. That one was painful to go because it took us a good minute to simplify these huge radicals and to simplify it in a really, really nice way so we can integrate it. And well, the next topic, what was that? Surface area. Those were a lot more challenging exercises to go. Well, fortunately, here arc length in parametric form, it's going to be a lot simpler. You'll see. Well, I'm going to derive this idea very, very briefly. So, and it's actually going to be a lot simpler than the derivation I showed you back in the arc length for functions of in defining rectangular form. We had to do some algebraic mischiefs here and there so we can actually obtain that dy dx. In this case, we don't need those algebraic mischiefs because, well, you'll see why in a minute. So number one, so we have the graphs of some function, whatever that is, it doesn't matter. So that's some function f that is defined in parametric form by two equations, the x equation and the y equation, that are both defined by or governed by this new third-party variable, which is t. And in this case, well, for the sake of simplicity, again, we refer to that t as time. But of course, there's other parameters that, again, you'll get to see them in Calc 3 next semester. However, in the meantime, well, let's look at this one. So we want to find the area, no, not the area, the arc length. So the arc length is the distance on a function from the point A to the point B. All right? And again, in a very similar way that we define the area under the curve back in Calculus 1 by chopping or partitioning the area of the region into rectangles and then refining that partition into pretty much infinitely many rectangles to get an accurate result. We did the same thing with an arc length. You know, for the arc length, we can have this length plus that length and do different partitions, but we can again do even more partitions, pretty much infinitely many partitions to get the actual arc length. And well, Well, I'm not going to do infinitely many partitions, of course, so I'm just going to do one representative partition here. And my representative partition here is just this length, okay? And I'm going to call this L. That's our length. Now, in order to go from point A to point B on this partition of length, it takes two things. The number one thing that it takes is some displacement in the x direction that I'm going to call delta x, and some displacement in the y direction, in the vertical direction, that I'm going to call delta y. Again, the uppercase delta symbol is always used to describe change in the same way that you use the effect in calculus 1 to describe the change of the variable y with respect to x and other applications, Now, the reason why we're not going to do this algebraic mischief the same way we did it with the other version of the arc length is because we can think about how these parametric equations are defined, and these parametric equations happen to be defined or happen to be governed by a new variable, by this third-party variable, which is t, or well, let's just call it t. So in this case, both delta x changes with respect to t the same way it changes with the delta y changes with respect to t. And well, did you see the picture that we have in there? Isn't that a right triangle? And we were looking at the sides of the right triangle. So the question for you, is there any formula or theorem or definition that relates the sides of a right triangle? Pythagorean theorem, right? Pythagorean theorem, that's c squared equals a squared plus b squared. And well, using our labels here, that's going to be L squared equals to delta x over delta t, quantity squared, plus delta y over delta t, quantity squared, and taking the square root, L equals to the square root of delta x delta t squared plus delta y delta t quantity squared. Isn't that this? Do you see this expression in blue? Doesn't that look somewhat like the integrand right here? Well, that's because, well, the next step in the process is to, well, because that expression I have in blue here is for the arc length of one partition, of one element in the partition. And again, if we want the whole arc length between A and B, we have to add infinitely many of these little lengths. And what happens when we add infinitely many of those? Where does that take us to? Huh? The integral, right? So that's it. That's where it's really coming from. Again, all these implications, the Riemann sum, the limit of n is infinity, and the like, right? But I think the most important is how we construct that idea from just a little triangle. That's all it is. All right. Let's look at one example. So let's go back to the cycloid defined by x equals 3 sine 3t, y equals 3 cosine 3t. Okay. So our arc length formula calls for the derivatives of both equations in this case, as opposed to the formula as opposed to finding the area under the curve. So number one, let's find the derivatives dx dt and dy dt. In this case, the derivative of, what's the derivative of the first equation? Anyone? 9 cosine, all right. That's a mini chain rule there, right? Cosine 3t. And what about the next one? Negative. Careful. Because the derivative of cosine is negative sine. That's negative sine 3t. And we have everything we need. We got everything we need to just set this up into the formula for arc length. L equals the integral from alpha to beta of the square root of dx dt quantity squared plus dy dt quantity squared with respect to t. And all we do is simply go from 0 to pi. And again, these limits of integration most of the times are going to be given. You won't have to figure out anything unless there's it's one of those weird problems in which you're giving other pieces of information. But well, typically they look like this. So that's the square root of the first quantity squared plus the second quantity squared dt. And those quantities here are number one, the derivatives, number one, 9 cosine 3t quantity squared, negative 9 sine 3t quantity squared. And well, at this point, you don't attempt to do any u substitution, because check that out. Take the derivative of the quantity inside of the parentheses, inside of the radical. There's really nothing outside of the radical that we can use as the du part. In fact, simplify the radicand and you'll see what's going to happen. It's going to simplify really nicely. You'll see. So that's 81 cosine squared 3t plus 81, again, negative quantity squared becomes positive, 81 sine squared 3t. We can factor out an 81, and you'll see the magic here. So 81 times cosine squared 3t plus sine squared 3t. And do you notice anything interesting here? What becomes 1? Exactly. That one becomes a 1. I know you guys might have learned sine squared theta plus cosine squared theta equals to 1. That's the basic identity that you might have learned, yes. However, this identity still holds through whenever the two angles are the same, even or if they're written in the reverse order, because we have an addition of terms in here. Sine squared plus cosine squared is the same as cosine plus sine squared. Doesn't matter. It works for sine squared 3 theta the same way that it works for, I don't know, let me make something crazy here. Sine squared of e to the sine root of x plus cosine squared of e to the sine root of x equals to 1. It doesn't matter what you have in the angle. Yes?
What if the theta for the cosine is different from the theta for the sine?
That's not the identity in that situation. We will have to use other identities. They're called the product to sum to products. Those are different identities. All right? So it doesn't matter what you have inside of the angle. As long as they're both the same, the identity holds true. And that's the integral from 0 to 2 pi. That's 81 times 1, which is simply 81. And the square root of 81, that's 9. So 9 times the integral from 0 to 2 pi. And what's the integral of dt? Just t, right? So 9t. Do you see how nice are these ones? How nice they simplify to? So 9 times 2 pi minus 0, that's simply 18 pi. All right? All right, guys. So, well, we have 5 minutes. Let me see. What about... So, let me briefly discuss what polar system is about. Of course, we're going to go more in depth next time, but essentially, what we're going to do in the polar system, we are going to describe a point xy in the rectangular system, but a point in the rectangular system basically does this. You know, if I want to go to the point 2, 3, that means I need to walk 2 steps in the x direction and 3 steps in the y direction. All right? In the polar system, however, we are going to graph points in a different way. So we're going to stand in the origin. From the origin, we're going to look towards the positive x-axis. That's going to be our zero, if you will, our reference. And instead of going x, y, we're going to go some angle and some radius and some distance to that point. All right? Well, I'd rather discuss all these details next time when we meet. So in the